Hello and welcome to Lesson 3. This lesson is going to examine the topic of generalised Newtonian fluids. That is to say, fluids where the viscosity depends on the shear rate of the flow rather than being constant. We're going to examine three different generalised Newtonian models: the power law model, the Carreau-Yasuda model and the Eyring model. All three of these models have certain strengths but also some weaknesses. We will see that analytical solutions exist for some common flow geometries for some models, but not at all for others. But let's start by explaining why these models are useful to us in the context of polymer processing. So we've spent a little bit of time in the past few lessons, especially at the start of the past few lessons, looking at examples of polymer processing operations. We've seen extrusion operations where you have a shape-forming process, where the shape that's formed might be a very thin annulus of a product, or it might be a slab of a product. And if one looks at extrusion dies for these products, we tend to have a great change of shape. We're going from effectively the barrel of an extruder to the shape that we're trying to form. And so what you'll see is that there's a very wide range of shear rates that are present, both within the extruder, as the flights turn against the barrel and there's very small gaps and very high shear, but also within extrusion dies, as you get this geometric change going from a very slow flow to a fast flow of polymer, and of course that fast flow infers a high shear rate. The crux of this is that a Newtonian approximation for polymer rheology is very rarely, if ever, valid. And so what we want to be able to do is to try and get a little bit more of a realistic model of what might be going on. Why might we want to do that? Well, we might, for example, want to estimate the pressure drops through an extrusion die. Or we might want to look at the shear rates within an extrusion die, because we might have a shear-induced crystallization process that happens, but only above a certain shear rate. We might want to look at the stress that's built up within an extrusion line because, well, stress takes time to relax. And if we know what stress we've got to start with, we can maybe make some estimate about that relaxation time. But I must underscore at this point that all the models we're going to be talking about for a generalised Newtonian model don't include time-dependent effects. They just include simply how viscosity changes with shear rate. And what we can do is sometimes use these models to understand what observation of a process is due to what base cause. And I'm going to give an example of that in the second part of this lesson. But let's start by thinking about how we can describe materials whose viscosity is not constant. So, if we have a look at how a Newtonian fluid might behave, and by behave I mean how its viscosity varies as a function of shear rate, by definition it's constant, as we can see on that graph on the whiteboard. If we contrast this with how a typical polymeric fluid behaves, we see something completely different. We see that the viscosity changes as a function of shear rate, and for polymeric materials tends to change in a fairly characteristic kind of a way. At very low shear rate, the viscosity is kind of sort of constant. We call that a low shear rate Newtonian plateau. We may have a region where the viscosity drops sometimes orders of magnitude with increasing shear rate. Again, that shear rate increase may also be of orders of magnitude. But then eventually what we find is that at very, very high shear rates, for example, the shear rates that one might experience in a thin annular extrusion die, the viscosity, or the apparent viscosity, is again kind of about constant really, and we call that the high shear rate Newtonian plateau. And so a typical polymeric fluid will go from high viscosity in the low shear rate Newtonian plateau, it'll go through a shear thinning region, and then it'll achieve its lowest viscosity, and that's in the high shear rate Newtonian plateau. Okay, so what's the simplest description we can apply to this that isn't Newtonian? So a simple description might be to acknowledge that in a typical polymer processing operation, we might have a lower limit on our shear rate and a higher limit on our shear rate. For example, those blue dashed vertical lines that I've put there on the graph. And that might be a typical shear rate range for a processing operation. And we can see within that range, our shear thinning region may be simply just power law. Okay, so that's kind of handy. So if we just drag that out, what we could do as an approximation is say, look, why don't we say that over the shear rate range of interest, our viscosity varies in a power law nature with shear rate. And we can write down a relationship for that. We can say our stress is some constant times the magnitude of our shear rate raised to a power n. Now, remember that shear rate is an inherently three-dimensional quantity, and the magnitude of the shear rate is, of course, the magnitude of a second-rank tensor, which I've put there in the footnote for you, just as a reminder. So we can go from stress to viscosity by simply dividing by shear rate. So viscosity is stress divided by shear rate. So therefore, eta, which is a symbol for a viscosity that is not constant, is simply that k magnitude of gamma dot to the n-1 now. And we can write the relationship between stress and magnitude of the shear rate by simply saying, well, let tau equal eta times gamma dot. It's kind of like our Newtonian relationship, but now what we're acknowledging is that eta changes with shear rate. Okay, fine. So this is a very simple departure from Newtonian behaviour. We can see that it's going to have a limited range of applicability, but over that limited range of applicability, we may find that one of the commonly available analytical solutions gives us an estimate, for example, a pressure drop or a shear rate, that is good enough to answer the question we're trying to answer. And remember what I said in the previous lessons, always know what question you're trying to answer and to what precision you require that answer. So, with key advantage of the power law model is you've got analytical solutions available, and we'll go over one of those in a second. Now, a key disadvantage for the power law model is this limited shear rate range. And if we think about what happens if we drop below that shear rate range, the first obvious thing that happens is that, well, for the real material, we enter the low shear rate Newtonian plateau, whereas our power law model predicts a viscosity that continues to increase, to the point where if we have a shear rate of 0, we have an infinite viscosity. And so from a numerical and computational standpoint, that's actually problematic because we get division by zero errors, perhaps during an iteration of a differential equation, which means that typically power law models, unmodified power law models with numerical codes, can give problems. Another key disadvantage is a key disadvantage that is inherent to all generalised Newtonian models, and that is it doesn't have anything included about elasticity or anything included about that time memory of elasticity. An elastic process takes time to build and time to decay, and none of that is built into this model. All this model predicts is that your apparent viscosity changes with shear rate, and with respect to the power law model, it changes in a power law manner. But as I said before, sometimes that's enough to be able to get us the insight that we're trying to achieve for a particular problem. So let's remind ourselves what a typical analytical solution for a power law fluid looks like. Imagine that we have flow through a pipe, as there on the whiteboard. We can, for example, derive the velocity profile. There you go. There's a statement of the velocity profile for a power law fluid flowing in pipe flow. We can, from that, also derive an expression for volumetric flow rate. And if you recall last lesson, the volumetric flow rate is simply the integral of the velocity field over the area. And what one finds is that if we've got a relationship linking volumetric flow and pressure drop, typically in an extrusion line we can set a volumetric flow rate, therefore we know that quantity and can infer what our pressure drop is through a pipe, for example. Now, there are a number of common solutions for power law fluids in various geometries. These are tabulated in the textbook that we're referring to for this course, which is Baird and Collias. Also, if you happen to have a copy of Dynamics of Polymeric Liquids, volume 1 of that series, table 4.2.1 has also some common solutions for power law flow in various geometries. Now, let's take a quick rain check. If what I've been talking about so far is a little unfamiliar, and if you look at the expression, for example, for that velocity profile and go, I can't remember how you get that, please go and look at these videos here and revise these concepts. Revise how to derive that velocity field, revise how to derive that volumetric flow rate, and I'll put the links to these videos also in the show notes to this video such that they're easy to follow. Now, let's move on to a generalized Newtonian model that better matches what we call the flow curve, the plot of viscosity against shear rate of a polymeric fluid. And we saw that typical polymeric fluids tend to have plateau regions, a low shear rate Newtonian plateau and a high shear rate Newtonian plateau. And there is a generalized Newtonian model out there called the Carreau-Yasuda model that captures this very, very beautifully. So the Carreau-Yasuda model typically is a good representation of the viscosity behavior of a polymeric fluid. And it's a 4-parameter model, and we can change those 4 parameters to match experimental data typically very, very well. The constitutive relationship that relates viscosity to shear rate is written as I've put there on the board. So typically one will look at the viscosity you've got now, eta, compared to those 2 plateau regions. So eta infinity is the viscosity of the high shear rate Newtonian plateau, it's low. Eta 0 is the viscosity of the low shear rate Newtonian plateau, it's high. And so in the denominator on the left hand side, eta 0 minus eta infinity is the total range of viscosity that the material changes over. So it's the low shear rate Newtonian plateau viscosity less the high shear rate Newtonian plateau viscosity. In the numerator, you've got the viscosity that you've got at your stated shear rate less the high shear rate Newtonian plateau viscosity. And we can see that that quotient is equal to, on the right hand side, a number of terms that involve a relaxation time, lambda, and you've got 2 other parameters there, A and M. And again, we can rearrange that relationship to give us eta, our variable viscosity, our variable Newtonian viscosity, and we can write our constitutive relationship as tau equals eta gamma dot, again with the recognition that eta is not constant, and we've written its variation right there. So a key advantage of the Carreau-Yasuda model is that it usually fits most polymer flow curves very, very well, and consequently you will usually find it implemented in numerical solvers. So for example, Polyflow or Rio tool within OpenFoam will have the Carreau-Yasuda model as one of its generalized Newtonian models. Now, a key disadvantage of the Carreau-Yasuda model is that, as far as I'm aware, there aren't any straightforward analytical solutions to it for, say, pipe flow or slot flow. So you always need numerical analysis. And again, in common with all the other generalized Newtonian fluids, it doesn't have any elastic effects incorporated within it. So let's look at one further generalized Newtonian model called the Eyring model. Now, the Eyring model was originally one of the first models derived from considerations of molecular theory, and it too actually captures the typical generalized Newtonian flow curve for a polymeric fluid, insofar that you have this low shear rate Newtonian plateau and this high shear rate Newtonian plateau, and then some kind of region of shear thinning connecting the two. So the Eyring model will adequately capture a flow curve. It has a slightly more complex constitutive relationship that I put there on the whiteboard for you. It involves inverse hyperbolic trigonometric functions, but that's easy to compute. And again, that will give us a value of eta, our varying viscosity with a function of shear rate. And so again, we can simply write that our stress tau is that varying viscosity eta multiplied by the modulus, or the size of, my shear rate tensor. So there we have that constitutive relationship. Now, in terms of an advantage, why use Eyring over Carreau-Yasuda, is that there are some analytical solutions that exist for the Eyring model. And we'll have a look at those in a second. And they may be useful in their own right to gain the type of insight that you're trying to achieve for the problem you're trying to solve. Again, just to reiterate, there isn't a solution to every flow curve for the Eyring model. You will have to use numerical analysis for anything more than just a simple pipe or a simple slot. And again, in common with every single other generalized Newtonian model, there are no elastic effects and there are no time-dependent effects. But let's just review a couple of the solutions to the Eyring model. Now, if we look at pipe flow again, a pipe with radius r of length L with a pressure drop across that length L of delta P, then here on the whiteboard is an expression for the volumetric flow rate. It's written in terms of a quantity tau r, and tau r here is equal to the pressure drop times the radius over 2 times the length. Tau 0 is a characteristic stress that is part of that Eyring model. There's also a solution for slot flow. If we have a slot of height 2h, and again of length L, and a pressure drop of delta P across that length L, we have another solution that we can use in terms of volumetric flow rate and wall shear stress. And the script character capital W there is the width of the slot into the screen, into the page. Again, if you want to learn more about the Eyring model, beyond what I've said here, have a look in Bird, Armstrong and Hasker's Dynamics of Polymeric Liquids, Volume 1, and Table 4.5-2 details some more solutions of the Eyring model. So let's look at what we're going to do in the remaining parts of this lesson. What we're going to do is firstly remind ourselves how we get to some of these analytical solutions. We're going to use Cauchy's momentum equation to set up an equation of motion for a generalised Newtonian fluid within a specific stated geometry. And we're going to have a look at, for example, pipe flow, and we're going to have a look at, for example, radial flow. Then what we're going to do is, where it's possible, once we've set that equation up, we're going to solve it. If it's possible to solve it analytically, we will. And the reason why is because analytical solutions have great utility, either in their own right as a way to solve or gain insight into a problem, or, and this is crucially important, to check a more complex numerical solution when the conditions of that numerical solution have been simplified down such that they will or should obey what the solution of the analytical model is. And so analytical solutions in this computational age are very, very, very useful for making sure that what the computer is telling us is actually a semblance of truth. Then what we're going to do is, using those equations that have been set up using Cauchy, we're going to look at one that we can't solve analytically, and we're going to solve it numerically. And I'm going to choose Mathematica as a numerical platform. The reason I've chosen Mathematica is purely for convenience. It's not my personal first choice. My personal first choice would be to code something up into Python or use MATLAB, but that requires an extra level of programming knowledge that this course simply doesn't have time to deliver. Mathematica is elegant. You can solve equations numerically with actually very little knowledge of numerical analysis. But if you're a competent coder and are you happy with MATLAB or with Python, do go ahead and use that. That's fine. But for the purposes of demonstration, I'm going to be using Mathematica. So let's summarize a few key points here. Generalized Newtonian models describe the departure from Newtonian behavior. The power law model, for example, is the simplest departure from Newtonian behavior. Newtonian behavior being that you have constant viscosity as a function of shear rate, where generalized Newtonian models describe shear thinning behavior. Remember, crucially, that generalized Newtonian models do not include elastic effects. They also do not include any time-dependent effects, such as stress buildup and stress decay. Analytical solutions are available for some generalized Newtonian models, and these can be incredibly useful for making approximate calculations or for checking numerical solutions. And on the subject of numerical solutions to flow problems are sometimes, some might argue often, needed, and it's a topic that we're going to explore in further parts of this lesson.